Okay, I think it's about time to start. So questions? Material? All right. So today we're going to sort of move on to the next chapter, chapter 3, book. And this deals with vector spaces. Now, these aren't disjoint like topics, right? So we didn't study groups and now we're done with groups. And, we want to use what we studied and kind of get to the more interesting parts of what we learned. Now, group theory is kind of a weird subject. So historically, how it arose is groups were sort of discovered as things that act on other things, right? They're sort of sets of symmetries of objects. That's how they sort of came out as something to study, as people studying some huge polytope in 3 dimensions, and they wanted to understand the set of symmetries of that and how it behaved, what they could learn about it. That's an example, but there's a lot of different contexts where we found them very useful. So the way to understand how a group actually interacts with the universe is to understand vector spaces and something called representation theory, which takes your group and lets it act on something, lets it actually be the set of symmetries of something. So what we need to do to kind of put those things together is get the other side of that equation, get vector spaces. Have a sense as to what those are. And I think a lot of you will have, this will be more familiar because you're taking some linear algebra, I assume. So, but we're going to try to do it a little more generally, a little more algebraically. So hopefully it'll be still of some use. Nonetheless, Artin starts 3.1 talking about the most familiar thing that people know in linear algebra, which is the vector space Rn. It doesn't spend too long. We're going to try to cover 5 sections this week. The first 3 are pretty short, but there's some interesting stuff. So we'll cover some of the first 3 today. The vector space of Rn. And this is the space set, if you want, of all columns, or sorry, row matrices. Column vectors, pardon. Column vectors with entries in the reals. As you all know, you can add these. So you can add column vectors, add these vectors. And you can scalar multiply. By something, say lambda. Now, in Calc 3 or maybe other classes, the notation that's used is, you have this kind of notation, like 2, 1. These are kind of the vectors, the way they're written. The notation we're going to use in this class, at least for when we write Rn, or R3 in this case, we would think of them this way. But everything else is the same. One thing I would say we don't have, I don't know if it's anywhere in Artin, but somewhere, but is there's this notion of a dot product, right? You guys all know that. That's actually kind of a subtle thing. Right? Dot products are so dot products are not sort of inherent to vector spaces. They're additional structure. So a dot product is some additional thing that you add on to a vector space, but as we'll see in a moment, they're not a part of the definition. So in order to have such a product, you need more. And they really are, in the geometric context, they're adding geometry to something that a priori doesn't have a geometric structure. what else can we say about this vector space? So we also can talk about the definition of a subspace. We say W is a subspace of R, and we'll have this in more general settings in a moment. I'm going to say if it's a non-empty subset, to be empty, and for any two elements, say W1, W2 of W, any element lambda of R, we have lambda W1 plus W2 is sorry, W. It's kind of a weird definition that I'm giving. It's slightly different, I think, than what Arden gives. But what you can conclude, so you can conclude that zero, the zero vector, let's write it 0, is in any subspace that you have, right? But you can multiply -1 times W and then add it to W. You'll get zeros in it. And of course, you can see that negatives are in any, if you have a vector, any scalar is times that vector is in this subspace. Because if it's zeros in it, take W2 to be 0, and you see that any scalar times something. And then if you just take lambda to equal 1, you'll see that the sum of any two vectors are also 1. So this is, being a subspace is just like being a subgroup. We want it to be closed under sort of the operations that we have at our disposal. Some vector spaces, we have two operations, not just one law of composition. We have two. We have one law of composition and we have something else, which is referring to scalars, whatever we call a scalar, which we'll get to in a moment. And those two things together, we want everything to be closed under those two laws of composition. So what is an example of a subspace that we want? Well, you guys, I think, spend some time learning about. Okay, so if A is an m by n matrix, we define null space to be all vectors let's call it x in Rn. Is it A times x with the 0 vector? This is the 0 right hand side is the 0 vector in Rm. This is sometimes, maybe also you can write this as the kernel of A. Some people write kernel, but I think in linear algebra you should call it the null space. And you can see that this does satisfy this property, right? If I have an x1, just verify. If I have x1, x2, this null space, then I multiply A times lambda x1 plus 2. We have this sort of distributive property. That matrix multiplication will distribute, but if you have a scalar, lambda is a real number, I can multiply, that sort of commutes with every matrices. Not matrices. Matrices don't commute with multiplication, but if you multiply with a scalar, it does. This will be lambda ax1 plus a2. But these are both in the null space, so each one of these is the 0 vector. So you get 0. So that shows that this is a subspace. So there's a proposition, I think it's just kind of to warm people up a little bit in this section, which is fine. I'll give a different kind of proof, but let's want to see if how people. There's a proposition. So just like with groups, we'll call something a proper subspace, like proper subgroup, if it's not too silly. There are two silly subspaces. There's the zero vector by itself. That's a subspace. And then there's everything. That's a subspace. So we'll say it's proper if it's neither of those two. So the proper subspaces are two are lines through the origin. Makes sense. Let's prove it.
Because it's the only one. Like the origin is the vector.
Okay, so yeah, so it certainly has to have zero. And so if it is a line, it has to go through the origin. So I agree with that. That's a good point. So we're not going to have some. So actually, there's this thing you've been told your whole mathematical life that's just a lie, and it's horrible. And there was a while where I tried to correct it, but then I just like said, fine, I'll just lie to you. Like when I'm teaching calculus. So the equation for what you find when you find an equation for a line in like middle school and high school and college, like that's not like a linear subspace, right? Like if I take the graph of a line, you say you've got a graph, it's a line. That's not a linear subspace. That's what's called an affine subspace. Linear subspaces, a line that's actually a linear subspace goes through the origin, like by definition. So because it's a subvector space of ours. So otherwise you call it, mathematicians call these things like flat, like translates of things that go through the origin. Those are affine subspaces. So yeah. So I always have this language. But yeah, so affine subspaces are not general. Or languages. Okay, but yeah, so why is it so let's say I have, so let's just say this. If I have a vector, right? If I have a non-zero vector, okay, and it's in a subspace, I can scalar multiply it. What am I going to trace out if I scalar multiply a vector by all the possible scales? All possible. So hold on. So I'm going to get, so let's go to the calculus. I have a vector. Whoa, I thought I could do this. I used to have this down. Ability, behavior set. There we go. Okay, so I have a vector, right? Like good old fashioned vector. And in our class, we're writing this vector as some mess. Now what happens in the first class of Calc 3 that I'll teach? I say, okay, what happens if I scale this vector? Longer and shorter. Is that all that happens? So I'm allowed to make it longer when I scale. I'm allowed to make it longer. I'm allowed to make it shorter. Yep, I can go the other direction. Now, if I take all of those values and I just do whatever I want with them, what am I tracing out? A line, right, through the origin. So what I want to say is, so let's let W be a proper subspace. and B, well, we'll say W, not equal to 0. This is proper. I know there's some non-zero guy in it. Element of W. Then lambda W, where lambda is any element R, line through the origin. We'll just say through W. You could say in the direction of W, but I want to stop using that language in this class. I'll just say through W. Of course, these are all, W is a subspace. So W contains this line. It contains all multiples, scalar multiples. So now the question is, well, what if it contains something else? So it contains the line, but could it contain something else? Let's see. Let's suppose, say, B is in W, but not on this line. Okay. So tell me, someone. So I wanted to introduce a little notation. So of course, it's not really notation, but we can take the transpose of column vectors and get row vectors. Okay, so let's take a transpose. Let's consider the following thing. We'll take W transpose, B transpose. So this is going to be, these are going to be 2 row vectors of length 2, right? We thought about them, we think there's just the Cartesian coordinates of W and B. We'll put them into a matrix, making a 2 by 2 matrix. What happens if I do row, if I put this in reduced echelon form? What happens to this matrix if I put it in reduced echelon? Yeah. Good question. That's fancy language, man. I'm not there yet. We'll get there. It's not assumed that people have a linear. So yeah. If V, okay, that's more like, right? So if V, well, if V is, what I want to say is if V is on this line, right? Then when I try to get rid of the first, entry here, it will also get rid of the second entry because it's the second whole row is a multiple of the first row. So that would, if V were in here, that would kill it. But if V is not in here, when I get rid of the first entry here, and I might have to permute to do that, the second entry will not be 0. Which means, what's the reduced echelon form? So I keep on saying reduced row echelons. Huh? Identity. It will be an identity, right? I only have 2 possibilities, right? I either have this, well, I guess I have 3 possibilities. I have this, or this. I mean, I guess I could have 0. Oops, 1. These are the 3. As long as I've got non-zero vectors, those are the 3. So I get the identity. Now what happens, what does that mean about this matrix? The solution? It's
means that in row operations, you can get like any invertible matrix from it.
okay, you said the word. It is invertible. It is invertible. It is invertible. So this is an invertible matrix. It's invertible. This has, and that's just for all. I'm not going to write that out, but I want to say this is invertible. It has a row echelon form. just by kind of eliminating the other options. So it's invertible. But that means that its transpose is an invertible, which is just this. Right? Something's invertible, then its transpose is invertible. Now let's look at the inverse. We'll say with inverse, ABC. So that means what? That means the identity is equal. Well, I'll multiply, I mean, inverse, you can multiply on the left or the right. But now, I mean, this is just because we're, oh, I'll just say. Right? Happy? In other words, I'm just, so this is, I can form this combination of these columns, these vectors, and get this vector, which will be the first. But now, as I said, a subspace is closed under scalar multiples and addition, right? Those are the two operations. So that means that this vector and this vector are both in W. But this vector is 1, 0. The other vector is 0, 1. This is our standard basis. This implies that we've got these two guys. 1, 0, 0, 1. W. But then if I take this linear combination, right, what do I get? I just get RS. For any RS. So everything. So that's not fair. Prediction. Okay. So the only thing is lines. I assume this will be used later on. I haven't checked that because it sort of reproves this theorem a bit later in the more general context. Okay. So this is all I wanted to say from the first section. It's not very long, just a couple pages, just reviewing some RN stuff. Really get going in the second section of chapter 3. Because now we're going to start being algebraists instead of people in 551. So what do we need to do everything we want to do? Not everything, almost everything we want to do with linear algebra. Because some people will say, let's talk about Rn. And you'll go and you'll talk to a physicist, any quantum mechanics at all, and they'll say, that's hogwash. You should be working in, well, Hilbert spaces over C. We're in CN or something, right? You should have complex numbers, right? Right. But, and you say, well, okay, I can do it. I think I can do everything I did in my class over R, but just use C instead. Just use complex numbers. You can do a lot. There's some subtle differences, and when you add those inner products, they become bigger differences. But actually, if you're just sticking with vector space, linear algebra, you can do everything that you want to do with R that you do with C. But now we're mathematicians, and we say, well, what about rational numbers? Rational numbers. We do everything we want with that. And what about other things? What if I put other entities in here? Besides, yeah.
You're not that closed under certain operations, but you do what we use the set of rationals to do it.
Well, that's the question. That is the question, really. What are those operations that we use when we do, for example, put something in row echelon? What do we do? Let me ask you guys that. What do we do, like, practically speaking? Elementary row operations. So what are they? Well, one thing we do is we just switch rows, okay? I don't care what entries I have in those rows, I can switch them, right? There's nothing I need to worry about there, right? What else do we do? Sorry? Addition, right. We will add like a row to another row, right? We can do that. So we do need addition. Now, what do we expect from addition? We expect that it forms an abelian group, right? We want to be able to subtract, like, right? We want to clear out that first entry. So we want to subtract off things. We want to add, we want all those rules that we have with groups, abelian groups, to be in place. Okay, so we want something that has an additive operation that is abelian, forms an abelian group. But let's just ask that question, right? If I have something like this, I want to do my first step of my row. I want to put something in row echelon form here. I don't need to switch rows here. I don't really need to add. What do I really need to do? I'm just saying, practically speaking, first step here. What would you do if you wanted to get this in row echelon form? Divide the top row by 2. That's great. So let's say exactly what you said, right? Divide. I want to divide. Dividing is a big ask, right? You can't always do it, right? We spent all that time talking about invertible matrices and so on, right? A lot of things aren't invertible. So we want a notion of division. So let's write down what our asks are here. So we want an operation plus that forms group. Now we also want a multiplication, which we'll just call in multiplication. This should also be an abelian group, right? We don't want to worry about commutativity, at least with the entries. I mean, it's one thing to be worried about the commutativity of like the actual matrices, but not with the entries. That's a bridge too far for now. It's actually very difficult. I mean, you can still do it for matrices, but okay, there's a lot that becomes more difficult to define. But yeah, what we would like is we would like this to form an abelian group too, kind of, because we want to be able to divide. But of course, there's one thing we can't divide, right? We can't divide by 0. Even in our good situations of reals and so on. So we don't really want this to form an abelian group. We want this to form an abelian group on the non-zero elements. And there's another thing we actually wanted. Maybe it came up, maybe the place that's coming in my mind. Of course, this is just fundamental and arithmetic things that we use, but one thing we talked about was like row linearity of determinant, right? We started talking about things like that. And this has a lot to do with like a sort of distributive property. We don't want these two operations to not know each other, to not have anything to do with each other, right? They should cooperate, at least in the basic ways that we expect. So we want some distributive property. I'm adding that one. We want compatibility between these operations, so distributive property. Which, as you recall, this is just this property. Okay. Turns out if we have everything I've written, then we have what's called a field. get what we want, we have a field. F. Then we call F a field. So what are examples? I've listed three. They're definitely the three most familiar. Yes. Yeah, the real numbers. That's the field that is, as I've said before, is actually a kind of complicated field. But it's the one that I think most people are most familiar with. See, what you learn about really first is the rationals. Maybe you learn about that in elementary school when you start doing fractions. And you struggle with like, what's the inverse of a half or something? 1/1/2. My son struggled with that. Too fast that. Complex numbers are. They have all of the properties. I mean, the only thing that maybe also takes a little getting used to is multiplicative inverse. I have, what is A plus B? Parenthetical. You do this, is this trick. Just, there's this thing called the conjugate. Take that plus and turn it. If you multiply a complex number by its conjugate, you get a real positive, non-negative. Okay, square the sum of the squares, the real part. So you can just see that this is, in fact, 1 over a squared plus. This is a real number, right? Assuming A and B are not 0. A minus. So we get multiplicative inverses. You can check that it's commutative, and as I've said before, beautiful field, really the best field around is the complex number. There's a certain point. So you had mentioned what a being close. So the fundamental theorem of algebra says that we should really work over C. And I've told you guys the fundamental theorem. You know the fundamental? Someone said it. I feel like I've got some vague memory. I just talk about it so much that I just remember saying. What is it? Fun. I mean, it's an algebra course. We should know the fun. Of course, it's sort of a misnomer because the fundamental theorem of algebra is never really proved in an algebra course unless you're at like the graduate level and then you prove it using like Galois theory, maybe. But what is the fundamental theorem of algebra? No, you guys learned the fundamental theorem of calculus, right? You learn the fundamental theorem of arithmetic, right? No, do you know?
With the primes.
Yeah, with the primes, that every number integer can be positive integer can be uniquely factored into primes. You guys learn. I mean, you know it because you're taught. But this is like it's like religious dogma, right? You're taught it in like elementary school, so you believe it your whole life. But there's actually a proof, right? I mean, there's actually a reason. So anyway, that's the fundamental theorem of arithmetic. There is a fundamental theorem of algebra. Actually, really way harder than all the others. Like, way harder. It just says so fundamental. Oh, let me just for your knowledge, right? Every polynomial coefficients in C, the complex coefficients. I should say every non-constant. Non-constant. As possibly complex. It's like has a solution. So in other words, you can always solve this equation. This was proven by Gauss, although some people may debate that, like that it was totally legit, but around 1800, like almost 200 years after. Like, this took a lot of work. It's not like people have been trying for a long time. Now there's all sorts of groups, and most of them involve like some kind of analysis or topology. This is more of actually a statement about sort of the geometry of the complex numbers. Okay, so we have these three examples. There's another, speaking of polynomials, there's another collection. Did anyone ever like, find it fishy that we called like principal parts and things like that with polynomials? We call like things rational functions. So there is another field like rational functions. That's a field. So these are just quotients, polynomial over another polynomial. They mimic the notion of rational numbers. Now, what's not a field? The integers are not a field. That's not a field. Because you can't divide by 2. Groups by themselves don't have enough structure. Groups are, one of the reasons groups are so hard is because they don't have this extra operation to kind of put the other one in check. Now there's another example. Natural numbers don't have group structure on. Natural numbers are none of it. They don't have, they're not a field, they're not. So this guy Z is called a ring, which we'll talk about later, but natural numbers aren't even a ring. Sometimes they're called a semi-ring. And natural numbers are awesome. In my book, I like studying things. This kind of stripped down properties, but they don't have enough to do. However, we have seen one more example, and it takes a different notation. The same thing, but it's because you're talking about something. FP. This is, for all intents and purposes, the same thing as Z mod P. P is not any number. That's a field. Now, why do we write FP? Because when I write FP, I'm saying I'm thinking of this as a field. I write Z mod P, I'm thinking of it as a group. Or even, I could think of it as a ring. I could think of it as like multiplying, but I can write things like Z mod 6. And that is not a field. So this is more like I'm not thinking of it as a field. This is notation to say I'm thinking of it as a field. I'm going to leave it at that. But they are identical as set. It's a different notation. FP is a field. Theorem. P is a field. And the only way when I write FP, I mean P is prime. For now. You can also take a prime power, but it means something. It is not Z mod that P. That's a different thing. So for now, I'm talking just FP, P is prime. It's actually proof. Well, we've shown that it's got these well-defined multiplication and addition operation. Everything is good there. No problem. We should certainly Z mod P is an abelian group under addition. And multiplication is commutative. And the distributive property holds because it holds in the integers. And we can just take representation classes and look at their congruence class. So if the distributive property holds in integers, it'll hold once we put that congruence class. So what's the thing that's missing? What do we need to show? What do we maybe worry about? I tell you it's a field. You believe me because you're very trusting people. But what do you leave saying? I don't know if I really do. What's the sticking point with the integers? Why is it not a field?
Divide inverses.
Yeah, I can't divide. I don't have inverses. Exactly right. I don't have inverses. So we need to check that. I did that check for the complex numbers just to make sure that you guys are finding the inverses. That's really the thing. Okay. That extra little having that multiplicative inverse for a field, life is so good. It's so good. Like you can do so much with just that little thing. And if you don't have it, life is so difficult. It's really a big deal. It's a big assumption. So let's see that we can do it. So we want to show that any A not equal to 0. I'm going to use the bars just to, right, for what we're talking about as an inverse. Multiplicative inverse. Well, tell me something about A and P. So note, the greatest common divisor here I'm choosing a representative of my congruence class, so A, just A. A, P is, drum roll please. Nice. 1. Very good. You guys are amazing. Why isn't it P? Why not P? Can it be P? A is, well, okay, I agree. You can choose A to be smaller than P, but what about 0? Well, A is not 0. We say it's not 0. So you're right. But in general, if A were like, bigger than P, we have that A is not 0, right? So A is not, 0 is the set of all of the integers that are divisible by P. So we're saying that A is not in that class. It's not divisible by P. P is prime. That means it's relatively. Okay, but yes, you're. So it's okay. Tell me about, I've got 2 numbers. They're relatively prime. What can I say about them? Anything?
Is that theorem like RS plus the other thing? Like
Yeah,
you
there's
you
that
have to be
theorem.
able to get one.
There's that theorem. Jesus theorem. Jesus. That warmed my heart right there. So there exists, I was going to say then there are integers satisfying this equation. Okay, let's take congruence classes. Or can someone tell me, can I make this more simple? For any congruence class that you know, any way to simplify this? These are congruence classes mod P.
So like the SP is just gonna equal 0.
Right, P is 0. P is divisible by P. Right? So this thing is 0. What is R called? Inverse, multiplicative inverse. Great. Bezu helps us again. So now what we see is that we always have a multiplicative inverse. I mean, as a part of the definition for a field. Now, if you have a weird situation, another thing I guess I want to say is that weird situations don't happen with fields, right? Like, so this is kind of a proposition. If F is a field, and A and B are elements of F, such that their product is 0, then one of them, either A is 0 or B is 0. The reason is because you have if they were both non-zero, you can multiply by the multiplicative inverse of one of them, and you would get that the other one is 0. So these things, when you have a situation where you can get A, B equals 0 and both are non-zero, you call these things zero divisors. So I'm not going to prove this. You can prove, I think I kind of verbally proved it more or less, but you can get it. If I look at something like Z mod 6, we can see this is not a field. Because 2 times 3 is 0. 2 times 3 is 6, which is congruent to 0. But 2 and 3 are not congruent to 0. So in particular, I mean, you can say, if I look at C mod n not prime, this is not a field. The same reason. Yeah.
Just a question about notation. When you put the bar above it, are you saying like mod, whatever?
Yeah, I'm taking the congruence class, which is that whole, it's just doing it working mod that number, right? That's right. So, and this is the same reason. Just take, 2 factors of n. You just take their product, that's 0, mod n. So, but they're not 0. The factors aren't 0. So I'm just trying to say, the only time we do get a field here is when we have this prime. Now, in the last minute, I just wanted to mention this. You can do, once you have a field, you can do a lot of the things we've been doing over that field. So we can talk about the general linear group over a finite field. These are very interesting groups. There are P elements in FP. And so if you look at GLN FP, this is a finite group. So you get a finite, and I think that in Artin, he kind of enumerates GL2 F2. This has 6 elements, and he shows, well, at least asserts that this is isomorphic, the symmetric group 1 through legs. So you can start kind of exploring a whole new class of groups once you start looking at these finite fields. Because all of the things, as I said, all of the things you did before with real numbers and complex numbers, you can now work over a finite field, or what's called positive characteristic. And we'll talk about positive characteristic a little next time. I think I'm about out of time, but yeah. So next time we'll continue talking about vector spaces and